Hi, everybody. Today we have our very own Da Fan. Da obtained his PhD in meteorology from Penn State University. He is interested in developing AI models for weather and climate applications, explainable AI, and uncertainty quantification. He's a LEAP postdoctoral researcher developing AI-based methods to identify climate model bias and automatically calibrate climate models. Da is currently based at NCAR in Boulder, Colorado, working on the LEAP project, attributing climate model divergence with hierarchical representation transformers with DJ Gagne. And with that, welcome, Da.
All right, thank you, Caitlin. Today I'm going to talk about my project on using AI or contrastive learning to identify structural bias or structural deficiencies in climate models and generate calibrated ensembles specific for warm rain microphysics. In climate models, warm rain microphysics remains a large source of uncertainty. This left figure shows many cloud processes like cloud condensation, the conversion from cloud water to rainwater and growth of rainwater. And in fact, many of these cloud processes are still poorly understood and can be directly resolved by climate models. Cloud processes have to be parameterized using empirical models. Um, Gettleman et al. 2021 developed a machine learning based microphysics scheme on the right that efficiently represents the change of cloud water and rain droplets using machine learning, which is here called tau-ML. And but however, when we compare the CAM6 model with tau-ML with compared to the observations, this CAM6 model still shows significant biases. You can see the large gap between the black curve and blue curve. So here's the example that here's the climatology comparison between the CAM6 with tau-ML in blue and observations in black. And the gap between the two, including the white part and the blue part, reflect two aspects in calibration. One is called structural deficiencies, that is from the limitation in the microphysics in the climate models and can be reduced. And the other is the parametric uncertainty. That is meaning the uncertainties in the physical parameters. So the objective of our work is to use AI or contrastive learning model to identify the structural deficiencies in CAM6 model with warm rain microphysics, and also calibrate physical parameters to better agree with the observations. So first, let me introduce the ensemble method we use, which is called perturbed parameter ensemble. So in this approach, we specify a set of physical parameters, and the range of each parameters is divided into multiple bins, and we sample the parameter values from each bin to generate a distinct parameter set. Then we run our physics model, the CAM6 model, with each parameter set to produce the forecast for each ensemble member. And here's the list of the 34 parameters we perturbed, including parameters for cloud turbulence scheme, the MG2 warm microphysics scheme, the aerosol scheme, and convection ZM convection scheme. And here's the data side we use. We focus on the variables, including cloud liquid water pass, short wave, long wave cloud forcing, net solar flux, and upward long wave flux. And we use the monthly mean variables from three different sources. The first one is the 100 member CAM6 PPE with KK 2000. Here we call it KK 2000 PPE. And so KK2000 is a default bulk scheme in CAM6 using CAM6 model with the empirical phase of cloud and rainwater distributions, and it's computationally efficient. And the second source is the 100-member TowerML PPE. So TowerML is a bin scheme for cloud and rainwater distribution with 35 bins. The original TAL scheme is computationally expensive because it consists of a distribution of many bins, but we replaced the original TAL by a machine learning version of TAL that is called TAL-ML, which is significantly faster, about 4 times more efficient than the original TAL. And the last source is the observation, the monthly climatology observations as a benchmark to evaluate which parameter sighting and which parameterization scheme is able to reduce the discrepancies relative to observations. And for the data split, we split the ensemble data into 3 parts. The member 1 to 60 is the training data, the member 61 to 80 is the validation, while the last 20 is the testing. So here's the contrastive learning framework. We use monthly mean variables from TowerML PP and KK2000 PP at 2 adjacent time steps, and corresponding monthly mean observation data. And we use a neural network to project. During the training part, we use a neural network to project monthly radiation and liquid water paths into a 128-dimensional latent space. So a latent space is a low-dimensional and highly compressed representation of the input data. And in the training step, the model pulls similar features in the latent space together and pushes these similar features apart. And after the training, we project the observations into the same latent space using a shared encoder just for comparison, and also as the benchmark. And then we use principal component analysis to further reduce the dimension from 128 to 3 dimensions just for visualization. So on the right, you can see the 3-dimensional latent space representation of TowerML, KK2000, and observation data. We have the TowerML in blue and KK2000 in right and observation in yellow. So it shows the features across months. You can see that TowerML and KK PP form 2 well-separated clusters, and while the observation is which is the yellow triangle, is generally closer to the TowerML, and this latent features rotate clockwise in this 3-dimensional space, showing seasonal variability. And we also found a strong correlation of this rotation, a strong correlation between this rotation and ENSO index. All right, any questions so far?
So I have a quick question. When you say,
Sure.
why do you use like 2 close together time steps as input? Or is that time step the month, or is that just?
Yeah, in that time step in months. And the reason why we were doing this is one assumption behind contrastive learning is that we need to feed them 2 inputs into the model, and these 2 inputs represent the 2 different angles or 2 different views of the same object. That's why we choose 2 adjacent monthly time steps. So that represents we have 2 different views of the same thing, because we have same parameter sightings, we have same microphysics scheme. So we assume they should perform similar in the latent space. Let me move on. So here's the architecture of the neural network encoder. So it's quite simple. So it's just we have about four convolutional layers and two pooling layers to extract features from the input and downscaling them to a lower resolution. Then we use three dense layers to further reduce the dimension from about 30,000 to 128. This 128 dimension vector just represents the latent space representation of the input. Next, we try to figure out the structural deficiency in the models through explainable AI. So here we define the latent space distance as the cosine distance. That is 1 minus the cosine similarity between data side A and data side B. So this cosine distance represents the angular difference in the latent space, and we interpret it as a low-dimensional representation of the structural differences. And it's actually a representation of differences in the global map of liquid water paths, long wave, short wave radiation. And here's an example of cosine distance between tau ml and observations from for ensemble members from member 1 to member 100. So a value of 2 a value of 2 means opposite direction in the latent space, or strong or large discrepancy, while a value of 0 means almost the same direction or a good similarity. So as you can see, most tau members have a really good agreement with the observations. And then we apply the explainable AI to the latent space distance, the cosine distance, to review which physical features drive these structural differences. In this attribution plot, so the right spots highlight where the model differs most from the observations. Then we go back to the input data and see whether these spots are really meaningful. So here are the structural differences identified by explainable AI for tau ML versus observations. So it's basically trying to explain the latent distance between tau ML and observations. And we found strong signals, you can see the right spots in many regions dominated by stratocumulus and shallow cumulus clouds. So which are the major structural deficiencies by our analysis between tau ML and observations? And then our next step is to do calibration with this latent space or latent space framework. So we calibrated model parameters using the latent cosine distance as the objective. Then we use a Gaussian process model to learn how physical parameters affect latent distance between KK or tau ML and observations. And then we use this Gaussian process model to generate 10 calibrated physical parameter size that minimize the latent distance with high confidence. So we did this calibration for KK 2000 and tau ML separately, and then we run the CAM6 model with this new calibrated parameters. And here are the calibrated results, and for liquid water paths, short wave, long wave, cloud forcing, upward long wave flux, and net solar flux. That's also the input of our contrast learning model. So you can see the black dashed line represents the observations. Blue is the original tau ML ensemble. The orange curve is the original KK 2000 ensemble. And the green curve is the calibrated KK2000. The right curve is the calibrated tau with the shading representing the ensemble spread. So after the calibration, we see clear improvements for both KK and tau ml. In general, there are better liquid water paths in the southern hemisphere, and you can see improvements in the tropics for the shortwave cloud forcing and nearly perfect upward long-wave flux after the calibration. We have slightly better net solar flux after calibration. And for the long-wave cloud forcing, the calibrated KK2000, this green curve shows improved agreement with observations, but the calibrated tau ml becomes a bit worse, which is likely a trade-off from the calibration. Any questions, comments so far? Okay, I'll move forward. Then here are the precipitation analysis for the calibrated ensemble. And I would like to thank Arisu for doing the analysis. So here's the histogram of precipitation for all members. So the green one is the iMerge observation data, which is the precipitation observation as the benchmark. And the orange and blue ones are the original KK2000 and tau ml PBE, while the red and green curves are the red and green ones are the calibrated tau ml and KK2000 ensemble. As you can see, this calibrated KK2000 has the best agreement with observations, and it's much better than original KK2000. And then the calibrated tau ml, this right one. So both calibrated results are much better than original KK and original tau ml ensemble. And I was a bit surprised that the calibrated KK performs better than the calibrated tau ml. So when I looked into the individual members, I found reason. So here are the results for member 1 to member 9. And we found large variability in the calibrated KK 2000. So you can see in member 2 and member 9, this calibrated KK 2000 show generate strong extreme precipitation that's comparable to the observations. But for the other members, you can see member 1, member 3, 4, 5, 6, 7, 8, this calibrated KK just show a poor representation of precipitation. So in some cases, it's better than the original KK2000, while in the others, like in member 8, it's even worse than the original KK2000. And in contrast, the calibrated tau ml shows consistent improvement across its members. So you can see in most members, this right histogram has a better agreement with observations than the other 3 ensemble. And then we try to figure out the reason for the improvement or the source of improvement by digging to the precipitation occurrence frequency, which is defined as the percentage of grid points where precipitation exceeds a given threshold. For example, here we show the frequency of precipitation that exceeds 0.02 millimeter per hour, so which is basically showing all precipitation. And here we have total precipitation frequency, a large scale or stratiform, and convective precipitation frequency. And the black curve is the iMerge benchmark, and the green and right curve are the calibrated tau ml and calibrated KK, while the orange and blue ones are the original tau ml and original KK. So you can see the improvements in almost everywhere. And we found the improvement um, in the mid latitudes, meaning come from their better representation of large scale precipitation, while the improvements in the tropics meaning comes from the better representation of convective precipitation. And then for the extreme precipitation, where we set the threshold to 1 millimeter per hour, we still see great improvements in the precipitation frequency, and still we found the improvements in the mid latitudes come from the better representation of large scale precipitation, while the improvements in the tropics mainly come from their better representation of convective precipitation. But we found this latent space calibration is still not perfect. I mean, it can reduce some structural error that we found by analyzing their global mean bias. Here are two examples. The left one is the global mean bias of upward long wave flux versus long wave cloud forcing. And the green points are the original 100 member PPE, while the right points are the calibrated PPE. So you can see these points are almost perfectly along a linear relationship between the upward long wave flux and long wave cloud forcing biases. However, this regression line doesn't intersect the origin, which means that it's not possible that to simultaneously eliminate the biases in both long wave cloud forcing and upward long wave flux, at least in our current experiments. And the right one shows another experiment that is the liquid water pass bias versus the short wave cloud forcing bias. So still these points are still far from the origin, and we can see this global mean bias is likely due to the structural model error rather than parametric uncertainty. Any questions or comments? Okay, so the last part I'll talk about a toy example. So we try to understand which difference is represented by latent features exactly. So we made a toy experiment, and we have a member A and member B. So member A represents the truth model, while member B represents a perturbed model. So both of them are simplified representation of climate models. So for each model, you can choose any parameter citing and structural bias for a given physics equation. So this is the physics equation, basically a combination of sine and cosine function. And so, as I said, member A is set as the truth, which has a fixed parameter setting and no structural bias. Member B has been added, was added 3 different perturbations or error. So in the first experiment, we added structural bias to member B. Then in the second one, we added the parameter perturbation. So we changed the parameter to the we changed the parameters used in the physics equation. In the last experiment, we changed the we added both structural bias and parameter perturbation. So in the first experiment, you can see we added the structural bias to the input, and then we run this simplified climate models over 100 time steps. Here are the results for member A and member B, and time step 0. And here are the histogram of the values over all time steps. So as you can see from the global map, the there there's a clear difference in the mean values. Um, as you can see, there are green spots in the member B, but compared to the nothing in member A. And in the histogram, you can see a clear difference in these two Gaussian distribution. So the member A has a mean value of about 3, while member B has a mean value of 5, and that comes from the structural bias we added to the member B. And after the normalization, here we choose a specific normalization method called per member normalization. We use the member A's z-score to normalize member A, use member B's z-score to normalize member B. As you can see, their normalized fields show a Gaussian distribution. And what it means in the latent space, I mean, we apply principal components to the normalized fields, and here are the representation of member A and member B in the latent space. And we found in the latent space, these two members are almost the same. And it's consistent with very low cosine distance in the latent space. So that means when we add the structural bias to the model, that doesn't change the representation in latent space significantly. All right, and the second experiment, we added parameter perturbation. So still we have the same physics equation, but we changed the parameters. Member A, which is the truth, still has the truth parameters and no main bias, while the member B uses perturbed parameters and still no bias. As you can see in the histogram for member A and member B, they look quite similar. I mean, similar mean values and slightly different shape. But in the normalized fields, we found some differences. For member A, it shows a Gaussian-like distribution, but for member B, it shows a bi-peak distribution, which is due to the perturbation of physical parameters. And then here are the latent representation of the normalized fields for the truth model and perturbed model. You can see there's a difference in locations and angle. And based on our calculation, the cosine distance or the angular difference between these two members are 0.16. So which means this parameter perturbation increases the distance between member A and member B in the latent space. And then the third experiment, we added both structural bias and parameter perturbation to the model B or member B. You can see in the histogram of the output for member A and member B, they show different mean values and different shape. And after normalization, still we see a Gaussian distribution for member A and a bi-peak distribution in member B. And the latent representation of the normalized fields looks similar as the one with only parameter perturbation. You can see the member B is in the inner circle, while member A is in the outer circle. And they have a cosine distance about 0.16. Okay, then let's put all these experiments together. You can see when we added the structural bias to the model, their latent space representations are almost the same. But when we add parameter perturbation or add both, their latent space representations change a lot. So the main takeaway of this toy example is that we think this latent space representation is a representation of the perturbed parameters or the parameter perturbation compared to the truth model. And we ignored the structural bias in our experiment by doing per member normalization, by doing by doing the latent space conversion. And of course, this is just a toy example. It's not the same as our complex climate models because the structural bias is not a constant in our real climate models. It could be dependent on many different factors, and the change of physical parameters it are not are also not the same as the ones in the real climate models. Okay, in conclusion, we design a contrast learning model to reduce feature dimensionality of physical features, specifically including cloud liquid water pulse and shortwave cloud wave radiation. And their latent space features show seasonal variability. And we apply explainable AI to the latent space distance to review structural deficiencies, which we found are primarily associated with stratocumulus and shallow cumulus. And we did calibration using the latent space distance with Gaussian process model or about Bayesian optimization. And the calibrated ensemble shows improved agreement with observations. And through our toy experiments, we found this latent feature representation is a representation of variations in physical parameters rather than structural bias. Yeah, that's all I have, and I'll take any question. Thank you.
Very interesting. I'm wondering, could you go back to your explainable AI figures?
Mm-hmm.
So I'm just curious, is this, so I think FLUT is long wave flux.
Mm-hmm.
Is that right? I'm just interested that you're seeing, are you changing something then in like deep convection or higher level clouds from these swarm rain? Or do you have an explanation for why this is also showing up in the long wave?
So the difference in the long wave upward flux is likely from the limitations in the models rather than some parameters we changed. So that means you can see the long wave upward flux. There's a gap between the original KK, original Talmel ensemble, and the observations. And this explainable AI is just trying to attribute these differences to some regions, but that doesn't mean we changed some settings that affects the high level clouds.
Okay, so this could happen even if you used, say, like K.
Yeah, so this structural differences mean this difference that doesn't mean something we can actually change by parameter tuning. It does mean some you can think this is a representation of both structural error and parametric uncertainty. And by doing calibration, we are able to reduce the difference in some spots, but it won't be perfect. So I would say some spots in upward long wave flux might represent some structural bias we can't change through calibration.
Okay, got it. Thank you.
Mm-hmm.
maybe if I can.
Mm-hmm. Sure.
So I'm interested in your toy model, and I think it gives very important information. So
Mm-hmm.
the result that you get from this toy model, how can you project it to your previous analysis? Like, can we say that most of the distance difference that you obtain is attributed to the difference in the parameters that we changed?
Yeah.
Or so?
Yeah, I think so. Yeah. I think from this toy experiment we can see the latent distance we used in both calibration um, and explainable AI or yeah are it is it's mostly attributed to the parameters, yeah, physical parameters
So
rather than yeah structure bias.
So basically, in your case, means like you use the KK2000 and tau ML. So the tau ML, the one that you introduced, is making this difference, is it? So the 100 ensemble members, the only
Mm-hmm.
difference between each members were like is one is with tau ML, the other one is with KK2000. So the distance that you got is mainly because of the difference that you introduced by using tau ML, is it?
No, I guess. So when we calculate the latent distance, for example, between KK and tau ml, this distance represents the difference in both skin and uh, physical parameters. When we calculate the latent distance between tau ml and um, observation, we think the distance comes from um, three parts. I think the first is the uh, physical parameters in tau ml. Second is the imperfect or the limitations in microphysics and climate models. And the third part is the observation, the imperfect observations. So because the real problem, I mean, the real climate model problem is more complex because here we have a truth and we have a simple perturbation added to the member B, but in our warm ring, in our contrastive learning framework, these three different data sources are quite different. Yeah.
Thank you.
Hi, Da. Great talk. So
Mm-hmm.
it's obviously we've been chatting about various aspects of this work. I think it'll be really it's great you're setting up sort of a more foundational or conceptual or I don't know, theoretical way to assess if latent space calibration is resistant to structural bias, to what extent it is, and if it can recognize it. Hopefully, I think moving forward, like, structural biases are never offsets. They're, as you sort of pointed out, they're regime dependent. So I do think like there's a lot of work to be done on this aspect that would be benefiting auto-calibration efforts in general. And hopefully we can figure out ways to add regime dependent offset. Calibration efforts can be resistant to those, bad effects and still calibrate parameters while not being susceptible to the regime dependent, structural biases. We have to I think it'd be really worth it if we think about ways to do that. And it might, at the end of the day, you might see certain signals that are indicative that can be sort of, tied to those structural biases. But anyway, it's great to see, especially this effort on, conceptual development of a simple model way of tackling structural biases and and to what extent that affects auto calibration. So that's great.
Yeah, I totally agree. Yeah. Yeah, I think if we can like identify the regime-dependent structural bias, and if we are able to remove those biases from the CAM6 outputs first before we do any calibration, no matter using history matching or any methods, then we will get stronger signals or stronger relationship between the 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 debiased fields and physical parameters. Yeah.
Yeah, exactly. Thanks.
Okay. In that case, Da, thanks so much for making time for us. It was nice to see you, and we hope to see you here in New York soon. And to all our guests, thanks for joining us. Have a great weekend.